So good morning, everyone. We are Group 9. My name is Caroline. I'm here with Jacob, Nikita, and David, and we will be presenting our process for finding the driving range of electric vehicles, otherwise known as EVs. So the problem that we are addressing is the fact that electric vehicle technology is not more widely used due to something known as range anxiety. This is the worry that the user will not be able to reach their final destination on the current charge of their battery. So the reason that this is unique to electric vehicles is because they have a longer charging time, fewer charging stations, unreliable predictions given by the EPA, and some of the research solutions currently available are very black box. So our process is a series of repeatable steps that generate an unbiased driving range estimate for electric vehicles. By following this process with a small EV, we are able to demonstrate that the output is an adaptable model that accurately predicts driving range based on a forecasted battery energy. So here we have some of the solutions that currently exist for electric vehicles. The top two solutions here are research-based and are very complex and utilize simulation as their method of validation. Below this, we also include some commercial solutions. The Tesla Basic Range Display is based on EPA predictions. EPA predictions are generated using a dynamometer, or basically a treadmill for a car, and they don't consider many real-world factors such as temperature. Below this, we also have the application for Tesla, which incorporates more factors, but is specific to only Tesla vehicles and requires a very large amount of data to validate. Our project is a physics-based battery energy model that has a complexity somewhere in the middle, so it's easily replicable, and it uses experimentation with our small EV to verify results. So in summation, compared to other research and solutions, our project has a novel way of applying both physics and experimental testing to create a comprehensible, but yet still very accurate model.
So here we have a brief overview of the 6 essential steps to our process. Now, we tested these steps on the scaled down electric vehicle, what we like to call the small EV, and later we'll go into how we do this process for 2-scale EVs. So let's get into the details of what we did for each step. For step 1, we have the physical model, and we used an energy-based model. So we found the battery energy using voltage and current readings. And we did that because the definition of work is equal to energy is equal to force times distance. So if we know the energy of a battery and the force that the battery is overcoming, sorry for my dog, which is the mu(n) static, or coefficient of static friction, times the normal force, we can then predict the distance. So once we find the battery energy, we can then calibrate a coefficient of friction using experimentally found variables, and then predict distance with that trained coefficient of friction that we'll get into later. The benefits of this energy model is that it takes into account all the variables listed below, and then we have the physics principles that we use to make this on the right. So for our experimental design, we have the small electric vehicle running in the top right, if you can see that. And that's hooked up to a multimeter for a current reading. And on the bottom, we have our outdoor testing, which we had a track of known distance, and we had subtrims, which are analogous to constant speeds. They're settings on the remote control, so we don't have to worry about repeatability. We have the set settings that we can do for each test. So for experimental testing, we ran the car to 100% to death. In the lab, which you saw, we ran it on a stool, so it wasn't going anywhere, there wasn't any resistance. And the purpose of that test was to calculate the baseline energy for each subtrim. And then using the same subtrims, we did outdoor testing, which simulates real-world conditions to find that coefficient of friction, as well as relate battery energy to temperature.
So once we have done the in-barn outdoor testing, we have the data necessary in order to basically construct our model and validate that it works. So what we first do is utilize the data to create a multiple linear regression model with the train test split, where we basically are predicting energy using subtrim and temperature. Then once we're able to confirm that this model is accurate, what we're able to do next is predict the energy related to each of the outdoor tests we do with known distance. Then we're able to solve our physical model for mu and calculate and basically train a value for mu. And then we can test that that's accurate, and then it predicts distance accurately. And we're able to confirm that with a low mean absolute percent error. Then what we do is once we validated that our model works because we're able to calculate with like low error, then what we're able to do is extend it basically to city, suburb, and highway cases. For each of these cases, basically we're trying to replicate what real driving is as much as possible. And one of the ways we do that is we follow like known standards. So for example, for city, we follow the urban driving cycle, which is part of the new European driving cycle, which is a standard for testing vehicles. And we do similarly, we're emulating real life for the suburban highway cases. Basically, what we do is we follow these profiles for lab and outdoor testing to get energy and distances. Then once we have that data, what we're able to do is extend it. And the way we do this is, again, train test. And we basically calculate a model for energy using only subtrim. It's a linear regression model. And then what we're able to do is using the measured energies, we can find an equivalent subtrim. And then we utilize that in our model, again, that uses subtrim and temperature. And it'll calculate energy and then predict distance. And we're able to get very accurate results. So then what we're able to do is, well, we aren't able to test on real EVs like perfectly. Like we are able to still use data that we have on real EVs. This data set that we use basically considers total energy, weight, and real range, which is the factors we need in order to train our model. And then what we're able to do is use the physics formula to come up with a trained model for mu. And then we're able to test that model and confirm that it's accurate, mu being the coefficient of static friction. So then we're basically able to confirm that's accurate. And the mu is a little bit different than the one for the small EV, but that's fine, given that there's like differences in the setup.
Moving on to the demo of the driving cycle extension with electric vehicle data. To validate our model, we collected large EV manufacturer data for the average driving cycle at the city, highway, and suburb driving cycles, the real range, and the battery energy. Then we calculated the average percent change from each driving cycle and the real range. So for example, the city range is about 21% higher than the real range. And next, we scaled the manufacturer's battery energy values with our calculated percentage changes to get energy predictions for each cycle. Finally, we applied our distance formula to get range predictions. And lastly, we analyzed our mean absolute percentage error and saw that this model has a high level of accuracy on large EVs. So therefore, our model is valid and can be extended to these large electric vehicles. The limitations of the project are as follows. So when we were validating our model, we had to rely on manufacturer's data because we did not have a large EV to gather test data on. In addition, due to time constraints, we could not account for all variables such as acceleration. Our overarching risk involves that time restrictions led to certain assumptions that we had to make. So we had to assume that the manufacturer's data was valid as the basis of our validation, and we were also unable to sensitize the coefficient of friction to different road conditions. However, despite these limitations, when we analyze our model for electric vehicle data, we can see in our graphs that our predicted ranges are very close to the actual ranges, which confirms that our model and assumptions are valid. So in conclusion, our deliverable is an objective and repeatable process that uses physics calculations to obtain accurate driving range predictions for electric vehicles. Going forward, if this project were continued, additional weather conditions could be tested and factors such as resistive force could be included to more accurately represent the coefficient of friction. Thank you for listening to our presentation, and a special thanks to Dr. Jafari and Dr. Shi for all their help this semester. We're happy to answer any questions.